Great, thank you for the great introduction and happy to be here. So today's talk is titled Space Fabric, Bridging Classical and Post-Quantum Security in Orbit. So I believe the last part in Orbit, it's kind of obvious, right? Like we are the satellite cybersecurity conference, but we'll try to unfold by what do we mean by many of the other aspects as well. So I believe many of you are aware that space is becoming a very interesting topic for multiple reasons. Many institutions from public, private sector are looking into sending, in general, more compute to space. And everyone is having their own strategy, like either we see the EU, NATO, but also we see more on the private sector side. Many people are sending more compute to space for various reasons as well, which is, of course, very exciting from my point of view. So what we see that the space is open for business, but also it's becoming a part of critical infrastructure, which should be and providing also a sovereignty layer, a defense domain, and also a increasing cyber-physical attack surface as well, which is something that we hope to cover in today's talk as a possible solution that we want to offer as well. So for those that are looking into the space for some time, we see that satellites themselves are becoming the compute nodes. More and more of the compute will be happening on the edge. We have to be storing keys, making sure that the policy engines that are being executed on the satellites are executed correctly. And of course, in general, they will be becoming a shared infrastructure where other people can go and execute their logic. And looking into the various stacks, we have the aspects of the secure communication, which we'll be diving a bit more into detail today. And then we have, of course, the logic running on the satellites themselves regarding proprietary AI algorithms and several others. And of course, ideally, once we have the base in place, we would like to see that there will be also dedicated space-native application and solutions where you can go and deploy your application as well, which of course will bring its own set of challenges. So when we look at the state of space security, are we there yet? We definitely see, and this is I think also why this is such a great venue to talk to, because we definitely see that there is a lot of motivation to see what we can be done with respect to security, because we see that there are many challenges that are real. One of recent study actually has shown that around 50% of satellite traffic is not even being properly encrypted, which of course, if you look at it, it's not an ideal number in general as well. And what we also see more and more, that the security across different missions is not really uniform. Many times the focus is on making sure we can provide and send more payloads to space. We try to make sure that the costs are lower with respect to the payload capacity and the rockets that are sending stuff to space, but sometimes security is not part of the main focus as well. Nevertheless, we know that space is become strategic infrastructure with respect to what it's providing, and become, from my personal opinion, become part of the strategic infrastructure faster than actually it become fully security mature infrastructure as well, which is something that hopefully is a great state, because it can of course be improved a lot moving forward as well. And with respect to that, we see that, of course, I'm not only talking about what we see in space, but also the communication between Earth and space as well. So with that, I would like to dive a bit more into the detail of the threat model. How do we actually communicate with space, and later on try to provide some ideas we have regarding the solution. So looking at the different type of threats we can be facing with the satellite technologies, we of course have to consider the link attacks. So of course we covered some aspects of jamming, spoofing, signal manipulation, eavesdropping on the general messages, which is of course a severe issue. We of course have to consider supply chain compromise. That of course is covering different aspects of the hardware, the firmware, the onboard software we have, and of course the cryptographic components. Then what we have to also consider, in case we want to go down that path, is to consider multi-tenant and hosted payload can also get compromised. So in case we have rideshare, it's great for many aspects, but possibly other parties sharing the same bus can have some issues with their software or hardware as well, of course. And even if you want to zoom in a bit closer, even if you have a shared payload, other people sharing the same payload don't necessarily have to be fully trusted. Then we also have the aspect of the challenge that we are talking about quite a heterogeneous infrastructure, right? We have some long-lived legacy systems, and we have some short-lived ones that are, for example, there for testing, and they go down to the atmosphere and burn after a few years. And also what is quite important is the cross-domain effects, where of course we know that we are using and sometimes looking into the infrastructure, providing different type of features from weather data, imaging, all the way to energy infrastructure that is used to communicate with remote areas as well. So now when we cover the the aspects of the threat model, let's try to unfold some of the components that will be relevant along the way as well. So first one is the PQC threat. I think I will try to skim over it a bit faster because previous speaker has covered some of the aspects already in quite detail, but at least we'll try to provide a general idea. So the post-quantum cryptography threat is especially prominent for classical public key cryptography. So for those that are familiar, this will be either the RSA-based solutions or elliptic curve cryptography solutions, which are under the hood relying on mathematical hard problems, such as discrete local algorithm or factorization of large numbers. And these problems are very easy to solve on a quantum computer using Shor's algorithm, or in case we talk about symmetric key cryptography such as AES, it's the Grover's algorithm that basically make this type of trap functions or hard problems very easy to solve in the post-quantum world. Which leads, of course, to the motivation to make sure that we are using cryptographic primitives that are very hard to solve on quantum computers. And for that, for example, if you look into the lattice-based direction, we are relying on the shortest vector problem and several others as well. Where actually are we using public key cryptography? It's actually, if you look at the infrastructure on Earth, but also for the one in space, it's using for key exchange mechanism. So this is the famous key exchange mechanism where we're actually establishing the symmetric key between the two parties, but we're also using it for authentication. So these are the signature schemes when actually you want to sign a certain message. It's authentic coming from me. It's part of the public key infrastructure. But it's also, for example, very much relevant for software updates, right? I want to make sure that only the software that is coming from me is being signed, and later on when it's being deployed on the respective end machine, it's being properly verified before it's being used. It's also relevant for command authorization, and of course, in general, collection of secure telemetry and mission data links as well. And of course, in case there will be quantum computer in the future, which seems to be at least sooner than later, at least from what we have seen, for example, in the recent announcements, big companies are shifting to post-quantum cryptography by 2029, especially after the recent announcement of Google. But more and more, at least the aspect of quantum readiness has to become part of the active area of implementation, not only research. And when we look at it, how is this currently being done? Of course, we know that the transition to post-quantum will most likely be starting in software. Developing your own hardware takes time, so you are usually starting with software solutions. And for that, it's very important to start to look into solutions that can be providing, that can be providing hybrid solution. So for example, major libraries such as OpenSSH or OpenSSL actually already are providing out of the box a hybrid key exchange mechanism. So you are protecting against harvest now, decrypt later type of attacks. And we see that actually more and more these type of formats of hybrid key exchange mechanisms will be becoming prominent. And what is also starting to propagate is the post-quantum cryptography certificates, where actually you are not only focusing on ensuring that the session itself cannot be harvested and later on decrypted, but actually also the certificates are much more difficult to forge as well, once you will be able to break the respective private key material used in classical cryptography. And this, of course, also comes with the general life cycle of keys, like either for algorithm negotiation, key rotation, and many others. And this is generally important that we actually start to think about this type of crypto agility. But also, I think, also important aspect for PQC. Even though we have standards now, the area is actively developing. We don't know for how long these standards will actually become these standards, because it's possible there might be some issues with them in the next few years, and we will have to go and actually upgrade again the respective software again to make sure it's implementing the state-of-the-art cryptographic algorithms again. So where do we see a possible practical architecture is to see how we can provide this type of crypto agility in having hybrid and upgradable form of solutions, which might be the safest path moving forward, where we have this staged rollout of classical cryptography for compatibility reasons, of course, but are adding more and more of this post-quantum cryptography in hybrid fashion, which I think is also interesting that we are considering that the software itself has to be upgraded. Meaning if we, for example, have a hardware firmware that later on has to be upgraded. It's also important that when we want to verify the hardware we want to verify the firmware that's being deployed in the hardware, there has to be like a small readiness aspect on the hardware front to be even able to upgrade itself. So overall, we see that it's taking some time, but it's important to keep up this agility as well to eventually have the option to phase out the vulnerable algorithms that will be relevant as well. So with that, we kind of cover the aspect on how do we actually secure the communication, because of course, post-quantum cryptography is very important, especially for the initial communication. And now we want to dive into the aspects where actually we are focusing on the orbital compute itself, which can provide new types of challenges, of course, because compute in space is not easy. We are constrained in power, in heat dissemination, and many others. But I think it can also provide very interesting future directions with respect to the research as well. And something that is quite interesting when observing what is happening in space is that many of the aspects that we see currently in the design, it's not generally built to scale by design. This might be a bit of a bold statement, but happy to hear your take on that one, definitely. But at least when observing it, what we see that generally we have purpose-built silos, where usually each satellite is designed, launched, and licensed for one particular mission and one particular customer. When we also look at some aspects with scarcity, they are actually becoming real issues, especially if you look at the launch slot capacities. So I'm not sure for whom of you has tried to recently go and send satellites to space, but it's definitely something that is taking quite some time to even get a slot and be able to launch it. And because of it, it's of course important to make sure that in case there is an increase in the demand, it's possible there is like also able to find a way on actually how we can scale on the front of not everyone building their own satellites, but see a way on actually how we can integrate and share resources with respect to that. And the other part is currently there is no clear orchestration layer that could be providing the synchronization, let's say, between different hardware in space and having ways and means actually how we can reuse this hardware as well more efficiently. We of course also see that space is becoming with unique type of opportunities. So once you're actually in space, it's very hard to go and physically tamper with your device, which I think is very interesting perspective with respect to having malicious party that actually can access your satellite, at least as of now. Depending from where you launch your satellite, you can also consider this aspect of neutrality with respect to the legal aspects. And as we have seen recently, of course, in case you have some local aspects of having issues with internet access, actually satellites, because they are flying all over the globe, can actually bypass this type of terrestrial exposure as well, which made them like a very unique backup infrastructure as well. And definitely what we see, there is a huge potential to decrease the cost, to basically make sure that more people can get onboarded into using space infrastructure, which of course can also lead into bigger speed improvements and hopefully also increase the state of security as well. So, of course, talking about security, we know that the economic answer is to share orbital infrastructure is cool, but of course, from a security perspective, if you are sharing, it's also becoming an aspect of security challenge because you are increasing your trusted compute base, and you have to find a way on actually how you can secure all of these type of infrastructure as well. And this is where we are introducing Space Fabric, which is something that we are considering as a way on how we could consider the security for the future. Very positive, very optimistic still in me. See how we can basically think about using this type of infrastructure as well. So looking at the ways on how users actually currently interact with the space infrastructure, you usually have someone who is having the terrestrial infrastructure, then they are using some form of gateway that can provide additional services. But also in general is the gateway that is there to make sure that you can deploy and communicate with different type of space infrastructure adapters later on the ground station, and eventually have your type of satellites that are your space infrastructure as well. Where ideal, of course, for us, we would like to see if we can have our own satellites, but of course we would be happy if other users are having their infrastructure, and they can follow similar workflow as well. Maybe before diving into the details, just a quick raise of hands. Who of you has heard before that about the technology called trusted execution environments? Great, quite a few of you. It's perfect. So just providing a short overview. So trusted execution environments, you can think of them as an isolated region in a CPU that is providing additional instructions that you as a developer can go and exploit. And in general, the idea is that they're providing a promising form of a environment. We can think of it as a vault enclave where you can actually run your code and also data. So maybe you have heard this term of data in space, basically. So in case you want to store your data on a disk, you can encrypt it. When you are transmitting your data, you also have the protection of data in transit, and confidential computing and TEs aim to provide the solution for data in use. So in case you want to do, for example, some training of your machine learning model or in general execute on the proprietary algorithm, you actually would like to have protection of data in use. And in general, this environment is providing also confidentiality and integrity protection to your application. But I think what is especially important feature of TEs, they're actually providing attestation capabilities, which means that not only myself actually know that I'm running in this infrastructure, but I can actually also generate a cryptographic proof that I can show to anyone else that actually the execution of my operation has happened inside of this particular enclave itself, which is a very attractive feature with respect to having this type of cryptographic proof that actually is telling you this is the case. If you're interested, I can provide more details on how does it actually work under the hood. But in general, you can think of it for now as a secure vault where if I deploy my code and my data, I can actually use it in quite an efficient way and do sensitive operation on it. We have published a paper recently called Space Fabric, which is the title of the slide as well, which is trying to provide a general overview of how actually a trusted execution environment architecture could look like in space, and I will try to unfold some of the aspects of the paper moving forward as well. So the general, I think, feature we are trying to focus on is to make sure we are actually generating the private keys in orbit. We are relying on the term that we try to coin called proof of execution triangulation, which is important from the part that the trusted execution environments tell you what code or data you are working with, but they don't necessarily tell you where is the execution happening. And of course, if you assume as a part of your threat model and your trust assumptions that the execution is actually happening in space, you need to have a way to actually identify the execution itself is really happening in space. And for that, we have introduced our own protocol, which you can have a look at in the paper as well. And to also look into the aspects of supply chain issues, we are combining multiple vendors to make sure actually we are having dual secure elements on board, that each of them provides different type of features as well with respect to the usability. So trying to unfold a bit more, why did we design Space Fabric, and the general idea with this in mind is in case you look into the trusted execution technology on Earth, there are a couple of issues with it. For example, we have a hardware root of trust that is usually in the manufacturer of the respective chip as well. So for example, in case we talk about Intel or AMD, usually they are part of the hard root of trust, which depending on the solution you are looking for might not be ideal. In general, every TE tells you what code it's running, but not where. This is the motivation why we had to look into the particular proof of execution triangulation. It also doesn't necessarily cover the aspects of the auditability and the supply chain issues. And I think the last one, which is also very crucial nowadays, is to cover the aspect of the post-quantum cryptography transition as well. So with these requirements in mind, we will try to make sure that the private keys are never generated on Earth. We are relying on a mixed hybrid approach of two secure elements for some of the operations, when one is actually completely open source. So if you know the design, you can actually go and create the chip yourself. And second one is more established from the perspective of the hardware manufacturer, but it's only a certified solution and it doesn't provide you the full traceability and auditability. And we have introduced this proof of execution triangulation as a way to actually bind the execution to the space environment itself. And with additional aspects in mind, we of course try to also make sure that the secure host operating system is very secure, very robust. We try to minimize the trusted compute base. And In case we have sensitive compute, we are actually offloading it through this trusted execution environment component, and we are providing the attestation to its users on Earth. So if you look at it, for example, from the perspective of the multi-tenancy, it means that me as a user, I can be getting a proof that my execution is really happening in space in a particular enclave. But it can also be very important, for example, for data that are coming from sensors in space as well. That I actually know that the data, image, sensoric, whatever you name it, is actually being cryptographically signed and can be later on consumed on Earth as well, which, especially if you consider different type of attacks, can be a very attractive value proposition as well. With respect to the post-quantum crypto transition, we actually purposefully picked certain elements that actually support already now the post-quantum cryptography readiness, so you actually can later on go and easily migrate to post-quantum cryptography enabled by the particular hardware. And we are actually also relying on the trusted execution environments as an intermediate step where actually you can store the post-quantum crypto keys as well, because there is enough space as well. And we also have a software-based solutions for actually having this attestation proof done in software as well. So with that, we basically kind of fully close the respective loop. And kind of coming back to the general purpose threat model, we are able to mitigate most of the challenges. So on the RF links, we are using authenticated and encrypted links that, of course, are also fresh for both crypto and post-quantum crypto. For the supply chain issues, we are actually having layered approach of measuring the boot and the attestation using open source software. And we also have multiple vendors in the loop. On the tenant front, we actually make sure that we can clearly separate the different tenants into these hardware enforced type of software boundaries, and make sure we can actually properly identify them. We are considering this crypto agility for both software and hardware updates in case you have a long-term satellite that you want to deploy in the future. And we also make sure that the attestation itself can actually provide you robust cryptographic proofs moving forward as well. So in summary, it's great to see that space is becoming strategic shared infrastructure. We hope that the space security will cover both communication, computation, identity, and supply chain. And we of course see that post-quantum cryptography is a migration problem, but it's not just an algorithm upgrade in itself, because there is a lot of stuff that actually are part of the overall workflow changes. And we hope that some of the ideas that are part of the paper can actually provide the improvements in this direction as well. So we are super excited about the current work, and we actually plan to validate many of the ideas in the upcoming missions, one later on this year and two at the beginning of next year as well. And with that, I would like to thank you, and we'll be happy to take any questions from you. Thank you very much.
Thank you very much, Filip. Very nice presentation. So do you have some questions from the audience? No?
Oh, sorry. No worries. Thanks, Filip. This is very interesting. I'm just wondering, so you're using TAE in this space to eliminate any side channel attacks and all of this. But I mean, do you care about how to communicate the attestation back to Earth? Is there any kind of sort of security that you, because it will use the same communication channels as, and you said, like it's mostly unencrypted, right?
It's a good question, and I have an answer for that. So kind of going back to this component, we actually would like to set up the secure communication channel between the solution we are calling Orbital here on Earth, which is basically a trusted enclave where actually we'll be running, let's say, the Earth-based infrastructure, where we will be terminating our secure communication channel, which again will be fully attestable and verifiable. And the intermediate components, such as like ground station, will basically just serve as the medium to forward the message, but the application layer protocol itself will be providing the cryptographic protection to any type of data going over this infrastructure. So it's kind of like a layered approach, basically, where the end-to-end secure communication channel will be established, for example, using MLCAM for making sure actually that we are also resistant to harvest non-decrypt later type of attacks. And the intermediate infrastructure will, of course, you need to have information on how to route the packets or the datagrams. But on the payload side, everything will be basically encrypted and decrypted only in the respective enclaves. Mm-hmm.
Okay, I think we had another question. No? Okay. So I guess that's it. Thank you very much, Filip. And thank you everyone for attending the session.
Thank you very much.